Alright, so now that we've seen a little bit of the exponential function in action, let's take a look at the exponential function algebraically. So we want to figure out how to get these two guys equal to each other. I want to figure out how to get this base to be the same as the base over here. And so we're going to write this as equals 10 squared. And since the bases are the same, then we can set the exponents to each other. And so here we can clearly see x equals 2. And it should be pretty obvious in this case that the x should be 2. Alright, now let's look at this one. Again, we're getting the bases to be the same. This is e to the 4th power, right? Because it's simply e to the 1 minus 5. I'm sorry, negative 4. E to the negative 4 right there. And so now that we have the bases the same, the exponents are now the same. So now we can see that x must be negative 4. Okay. So far, so good. This next one, a little more tricky, but not too terrible. There's actually more than one way to solve this. What we're going to do is we're just going to divide both sides by 5 so that we have 1/5 raised to the 2x equals 1/5 to the 1st power. So now we have the bases that are the same, so we can set the exponent equal to each other. And so we have 2x equals 1, so x must equal 1/2. Now there is another way that we could have done this. We could have, instead of using 1/5 as a base, we could be looking at to use 5 as a base. And if we do that, then we'd have 5 to the negative 1st power here, times 2x, times 5, equals 1, which is really just 5 to the 0th power. All right, so then this becomes 5 to the negative 2x, multiplied by 5 equals 5 to the 0, and then this becomes 5 to the negative 2x plus 1 is 5 raised to the 0. Now we have equal bases. And so we can set the exponents equal to each other as well. So we got negative 2x plus 1 equals 0, solve for x, and we get that x again equals 1/2. Okay. Two different ways, same problem. Alright, next one. We have 1 over the square root of 2. Again, we've got two different ways to solve this one, but we'll start with this one. Divide both sides by 4, and we get 2 on the right-hand side. Alright, so now we want to get these bases to be the same. We can go ahead and take this square and bring it inside. And so when we do that, we get 1/2 raised to the x. And we can also rewrite this as 1/2 to the negative 1. And so then we have bases that are the same, and so now we can set the exponents to the same, and we can see here that x does in fact equal negative 1. Alright, there are multiple ways to solve this one. I encourage you to try a different way on your own. Just know that even though there are multiple ways to solve it, there is only one correct answer, and that is x equals negative 1. Alright, so now let's go on. Now that we've got a feeling for the exponential function, let's go ahead and talk about the logarithmic function. One thing that you know about the base function always looks like that, right? We've been using 2 for the base, but the exponential function, you know, it can be any base. And of course, a famous one would be e raised to the x. Alright, so let's take a look here. At the logarithmic function. What does the logarithmic function do? So basically, this is saying that if you've got a b right here, you know, like whatever your base is, what exponent do I have to put on this base in order to get a, right? Log of b of a equals c. So c is going to be the base. So b raised to the c equals a, right? What exponent do I have to put on b in order to get a? All right. So let's take a look at this. Log base 2 of 4. What exponent do I have to put on 2 to get 4? Well, I need a 2 exponent, right? So the answer to that question is 2. All right, and if it was log base 2 of 8, well, that would be, log base 2 of 2 to the third power. So what exponent do I have to put on that 2 to get 2 cubed? 3. All right, this next one, there is no base. What does that mean? That means this is a common log. It means that it's got a base of 10. So anytime you don't see a base written down, that means it's a common log and that it's going to be a base of 10. All right, so we had a common log of 10 raised to the negative second power. So the answer here is negative 2. All right, now here we got what's called a natural log, ln. So a natural log is log with a base e. That's all that means. So what exponent do I have to put on this e to get e to the 13? Well, the answer is just 13. Okay, now let's look at this in the general case. Log base b of b raised to the x. Well, that's just x. Clear enough. Now, I want us to think about this for a second. If we say that f of x equals log base b of x, and if I say g of x equals b raised to the x, right? We got a logarithmic function and then an exponential function. And let's say we do this, right? We run one right after the other. Well, this is f of g of x. Well, that's the same thing as saying log base b of b raised to the x. And that equals x. Inside equals the outside. What this tells us is that we got an inverse function going on. We've tested it one direction. We need to test it the other direction to make sure that the inverse does in fact hold. All right, so here we're going to be a little tricky to see what's going on in the other direction. All right, so now we're over here. Note that this is equivalent to saying, well, what is g of f of x? The way we've defined it over here. And so what we're going to do is we're going to take the log base b of both sides. Right? And so just make sure you see everything. That y goes here. This whole thing is this whole thing right there. All right. So what exponent do I have to put on this b in order to get b raised to the log base b of x? Well, clearly it's just log base b of x. Okay. So note that log base b of y, log base b of x, they both match each other. And this would indicate that y equals x. So in other words, anytime you see a y, you can replace it with an x. So this means that g of f of x, which becomes b log base b of x, means that equals x, right? Because that becomes x. So note that we've tested this both ways, and so we see that the logarithmic and the exponential function are in fact inverses of each other. Okay, so let's go ahead and graph these three in Desmos. Alright, so first function we have is y equals b raised to the x. Now let's go ahead and graph y equals x. Make this a nice dashed line. Then y equals log base b of x. And so note that we have this nice symmetry going on, right? Right about the line y equals x. This is exactly what we would expect to see from two inverse functions. And so let's go ahead and turn this into a slider. So you can see, that no matter what base we pick, so long as we're positive, we're not allowed to use a negative base, you see, or base 0. So which is why I've selected the range of the bases that I have. But you can see that for the given range, no matter what b we pick, these functions are always inverse functions of each other. And so what symmetry do we notice? Symmetric about y equals x. So we would say there is some inverse symmetry. That second m doesn't look right. There we go. So we have some inverse symmetry going on, the kind of symmetry we'd expect from inverse functions. Okay, so we've got some logarithm rules right here. I think, given that I've hit you guys with quite a bit already, I'm going to hit the pause button on here, and we will go over these logarithmic functions tomorrow.